now, right? So here, each of these stars can either be a digit between 0 and 9, or it could be a bit between 0 and 1. I don't really care. What I'm going to tell you is going to be the same. How do you add? You add these two. Oh, here's Tom Lear, is a mathematician who has great songs, and I listened to him growing up. All right, how do you, I need to fix this slide. You're supposed to add those two and carry, right? Then you add those three and carry. Then you add those three and carry, right? Everybody, how long does it take to add 3 and carry? Constant time, right? How many times do I have to do it? N time. What's the running time of this algorithm? Order n, right? Everybody see that? What? Oh, sorry. How long does it take me to do one loop, right? To add these 3 and carry. One iteration takes me constant. Yeah, sorry. It's constant to do one of these, and I have to do n of them, right? So adding takes order n time, right? And we call this, I call it the grade school algorithm, right? I don't know when you learn it. Maybe it's not until high school. No, surely you learn it in grade school, right? All right, everybody good? All right, so here we can ask, and I think I've asked you this question already. Is it possible to add faster than, if you have n digits, can you add time faster than order n? Can you run it in time square root of n? Can you do it in log n? All right, so here, let me answer the question. It takes you order n time just to look at the input, right? And if you haven't looked, right, because all I can do is look at one number per iteration, right? So it's going to take me n time just to look at the input. And if I haven't looked at the input, I don't know the answer, right? So that says you can't do it faster. Does that make sense? I mean, you can get the constant down, right? But you can't get the order n down, right? Everybody good? All right, so this just says, now we know the exact time complexity of adding, right? You can do it in order n time. You can't do it faster, right? Everybody good? Let's move over to multiplication, all right? Again, we have 2 n-digit numbers. They could be in bits. They could be in decimals. And basically, how do you do it? It's you take this number and multiply it by all of those, and you write it here. And then you take this number and multiply it by all of those and write it here. It's shifted, right? Bottom line is every digit here gets multiplied by every digit here, right? This is the high school algorithm. Everybody agree? What's the running time of this high school algorithm? O of n squared, right? I gotta compute all these n squared things and then add them up, right? Over n, right? So there. It takes order. So now that we know that multiplication takes order n time, order n squared time. Do we know that? Do we know that its time complexity is order n squared? Maybe you can do it better, right? Can you multiply faster? Right? Okay, how do you multiply faster? Oh, perfect. Perfect. Why do they teach you, what grade do they teach you this in? Kindergarten, maybe, right? They teach you this later. if this is a better algorithm, why do they even teach you this one? It takes a long time? Well, that's the puzzle here, all right? What we're here studying is time complexity, right? So let's figure out the time complexity of these algorithms, all right? Right, so how do you multiply? Everybody gets this multiplication algorithm? You add A, B times, right? Let's say I'll let you add in constant time, right? I'm really nice to you. So the running time is order B, right? Is that linear time? All right? This one's quadratic time, and this one's linear time, right? Does that feel right to you? Feels right to you? All right, I'm going to test you. Which is faster? Okay, I'm going to lock you in a room, and you can't come out until you multiply these two, right? Could you do it using this algorithm? Yeah, paper. You could, right? It would take you a long time. You would hate me, but you could do it, right? Could you do it using this algorithm? Right? Absolutely not, right? In this much time, you'll be dead, right? Everybody see that? So this algorithm is clearly worse, right? And we want our time complexity to reflect on the fact that it's clearly worse, right? Yet this one says linear and this one says quadratic. You know, he even came up with this was a better algorithm, right? But it's clearly not a better algorithm, right? Right, so you can ask, how many minutes does this take? How many centuries does this take? It's bad. Now, let's look at another thing that we can do. Remember I talked about incremental? Let's make my input 1 digit bigger, right? How much does this time increase by? Yeah, you're going from n squared to n plus 1 squared, right? The derivative of n squared is 2n, right? It's going to take you 2n more time. Why? Because this extra digit, you get an extra digit, you got to multiply it by all of those, right? Everybody, this goes by n squared. An additional plus n squared, right? How much does this time go up by? Ten times. Your running time just went up 10 times. Which do you prefer? 10 times is bad, right? It's bad. What things go up exponentially? I said the answer. What things go up 10 times, right? Exponential functions, right? So that comes down to, why is this an exponential time algorithm, right?